Hello everyone, welcome and thank you for joining this month's Seequent Tech Talk, Seequent's integrated workflow for investigating slope stability in open pit mines. My name is Sophie Tai and I'm a geologist with Seequent, and my co-presenter, Farzan Hamidi, is a geotechnical engineer with Seequent. So I will be presenting the introduction and first half of today's Tech Talk workflow, and Farzan will take over with the second half and provide a summary and conclusion. So this slide provides a summary of Seequent's integrated workflow for investigating slope stability in open pit mines. And as you can see, the workflow makes use of Leapfrog, Central, and Geostudio. At the beginning of the workflow, data is imported to Leapfrog, Seequent's 3D implicit modelling software, to create geological models or geotechnical domain models. Leapfrog allows users to add new data quickly, keeping models up to date and up to speed with project life cycles. Leapfrog allows users to see and work in 3D to bring instant clarity, aid understanding, and it allows users to easily communicate and collaborate. Additionally, and most importantly for today's workflow, Leapfrog also allows users to rapidly create dynamic serial cross-sections in desired directions and offsets for use later on in the Geostudio workflow. Leapfrog integrates with Central, so once completed, the Leapfrog model or models can be published to Central, Seequent's cloud-hosted data and model management solution. And it's in the Central environment that users can visualize, track, and manage data from a centralized, auditable environment. Central brings project teams such as geologists and geotechnical engineers and critical project data together. It allows users to stay connected and actively collaborate and communicate decisions, all in an environment that has industry best practice for security backup and disaster recovery. Central also integrates directly with Geostudio, so projects and sections that have been published to Central can be seamlessly downloaded directly to Geostudio projects, negating the need to recreate geometries and reassign regions. Once imported to Geostudio, material properties, boundary conditions, and piezometric lines and slip surfaces can be added to the imported Leapfrog sections. From there, limit, equilibrium, finite element, stress-based, and strength reduction analyses can be undertaken. So, to summarise this workflow, today Farzan and I will show how Leapfrog is used to create geological or geotechnical models and rapidly generate serial cross-sections in desired directions and offsets to be used for slope stability analysis. Projects and sections are then going to be published to Central, which allows users to visualize, track, manage the model and all of the associated data, while also ensuring the models and sections can be seamlessly and directly imported to Geostudio. And then finally in Geostudio, sections are obviously seamlessly imported and analyses are set up and run. You'll note that data can flow in both directions, see those arrows going both ways in and out of Central. So this means the workflow can be iterative and that, for example, the solved analyses in Geostudio can even be imported back to Leapfrog via Central, allowing for 3D visualization of analyses in the Leapfrog environment. So I'm going to jump into Leapfrog now and show you the Leapfrog and Central part of the workflow, and then Farzan will take over once we get to the Geostudio part of the workflow. So here we are in Leapfrog. I'll just talk you through the project quickly by showing you some of the objects in the project tree. For those who have not seen or used Leapfrog before, the project tree on the left-hand side of the screen is a series of folders that are used to generate or organize objects, such as datasets, maps, and images into various categories. These folders also provide tools that let you import information into the project and generate models. So starting at the top with the topography folder, I've generated a mesh or surface representing the topography, as you can see in the 3D scene here. And in the drill holes folder, I've imported our drill hole data, which includes our drill holes that have been logged for geology. Moving down the project tree, in the meshes folder, I've imported a mesh or a surface of the pit design. And in the geological models folder, I've created two models. Now, don't let the name geological model trip you up. Models created in this folder are just models that have been created from categoric data. So in addition to models that are based off geology, we would also create models based on our geotechnical domains. For example, in this folder, weathering models, alteration models are other examples. We're essentially just creating geometries that represent domains. It's common for geotechnical domain models to be built off existing geological models, so lumping geological units together or perhaps splitting them up based on their geotechnical parameters or material properties. The first model you can see is the hop-toed geology model. See what I did there? Which has been created off the drill hole data. It's possible to use Leapfrog's slicing tool to cut sections of the model, which we can step through to gain an appreciation of the ground conditions below surface. So I'll just clear my scene now. The second model in my geological models folder is the pit shell model. This is a very simple model I've created from our pit mesh, just two domains, which are the inside of the pit and the outside of the pit. The reason for generating these two models is it allows us, or me, to then create a model that includes the geology on the outside of the pit only. So with the inside of the pit removed. And that means we can, or Farzan can then undertake our stability analyses of the pit walls in various orientations. So if I come to the combined models folder, you can see I've created a combined model, which does just that, a geology model of the inside of the pit and a geology model of the outside of the pit. Now lastly, I'm just going to open the cross sections and contours folder to show you some serial sections that I've created at varying orientations to the pit walls. Serial sections are quick and easy to create in Leapfrog. Essentially, we create a single base section and then create the series or the other sections at an offset from this initial base section. These sections have the geological model evaluated or displayed on them, and we can evaluate other objects onto the sections as well, for example, our pit mesh. So that's the quick overview of this project. Once the project has been created or completed, the next step is to publish the model to Central, and that's so Farzan can access it directly from Central in Geostudio. So this removes the need to export multiple sections as DXFs, save them to a location on my C drive or a network drive perhaps, and then import from there into Geostudio. It also means that if I update the model in Leapfrog and publish it to Central, Farzan can automatically update the model in Geostudio because everything is already linked. So to publish to Central, I navigate to the Central button in the top right corner of my screen, ensure I'm connected to the Central server that I want to publish to, and then hit Publish. Coming back to my Central tab in Leapfrog, here's a summary of the project to date. You can see that Each node in the project history represents a publishing event or a revision of the model. So you can see this project has seen numerous iterations or updates or revisions to the model, which means we retain a digital audit trail of how the model or the project has evolved over time. And additionally, we can see there are several branches. These are useful as they allow different hypotheses to be explored. Branches are pretty flexible and central. They can be adapted to suit your workflow. They can also be locked, like the geology branch on this model, which means users other than the person who locked the branch can't work on that branch until it's unlocked again. Data can also be shared between branches and other central projects in Leapfrog. So, if I wanted to take an object from a model on the geology branch and import it to a model on the geotechnical branch, I could do that. I'll just quickly open the central portal. So in here we can see our project overview, where the project is located, what users can access the project. I can see all files or data related to the project, so these are all saved in their appropriate folders in the central data room. I can see the full history of the project and any saved scenes. These are essentially just bookmarks of the project, and we can open these in WebViz and look at our project in 3D in a web-based environment without having to download or open the project in Leapfrog. So good for reviewers or seniors or management. WebViz is also where we leave comments for each other. So now that the project has been completed and uploaded to Central, I'll now pass on to Farzan to demonstrate the next part of this workflow and to summarise and wrap up today's session. Thanks.
Thank you, Sophie, for the great introduction, and welcome everyone to today's month's Tech Talk, integrated workflow for investigating slope stability in open pit mines.
We open up the Geostudio, a new version of Geostudio, which is revision 4, and by clicking on New and selecting the units,
then we will add a 3D geometry into model, and then open up edit with build 3D, open up the build 3D environment. In the build 3D, we can import those sections that Sophie created. We can either import them from central or from the file. We select from central and select the right central instance, which is APAC demo for this one. I select that, and I will select the project name, the next stage. It is integrated workflow. And for the next one, I select the branch, which is the geotechnical analysis. And it's better always to leave the ID as the latest one. If we want to reload the section, we can simply do that. As you can see all the sections that Sophie created here. You can select to import them all, or you can import them one by one. As you can see here, I will select just the northeast, southwest one, and then I will show you how to import the second one.
So once you click on OK, you will see the cross-section imported into build 3D. As you can see, these are the similar cross-section, but since the build 3D has a different actually coordinate systems, when you compare it with the Leapfrog coordinate system, which we have a Z coordinate on the depths, we have Y coordinate in Geostudio as a depth. So we are going to convert this, do this right conversion, and once we adjust these coordinate system, we are going to adjust just the base point, and once we adjust the base point, Geostudio automatically find the right location to put all the cross section in the view. So you can simply see that all the cross sections are imported into Build3D, and once you click OK, you will be able to save the import, and then you will be able to export it within the similar coordinate conversion. So as you can see, all the lithological units, all the colors are transferred, all the geometries are transferred within Geostudio, and you can simply see all the material and you can select them, each of them, and once you select them, you will see them highlighted in blue. For example, the dike, once you click on that, the internal dike, we separate the inside and outside the pit. So you can simply click on the dike inside the pit and outside the pit, and it will be continuously showing. Or you can see the ore body inside and outside the pit. So you can simply realize how much ore you extracted and how much you leave the ore inside the medium. So you can simply close this icon and then go back to cross section. So we would like to create these cross section and generate them. Before doing that, we are going to simplify the line segments that are created this cross section. All the line segments are imported into Geostudio, but we simplify it by this number. So by 5 times we simplify it, and as you can see, once you select that, it will generate the 2D cross section from the 3D geology. So you can simply see all these sections within the pit, and the pit geometry also included in our cross section. So let's get back to the Build3D environment. We are going to import this time the second series of our cross sections.
So you can see the same procedure is followed to import the second series of cross section.
Once you import it, you will see it in a wrong coordinate system. You just need to simply select import 2D section that we already save it, and then it will convert it into the right coordinate. We don't need to select the adjust base point anymore. And then once we select OK, that's it. So all the cross section all imported into Build3D, and then we can generate a 2D cross section and use them as an input parameter in a slope W or sigma W or SIP W analysis.
Then we follow the similar procedure to generate cross sections.
We just close the Build3D, and we will see all those new cross section appears in a 2D cross section as a child analysis to the 3D geometry.
The next step is to select the section to start with. Then we add a physics, which is here is SIP-W for modeling underground flow. So we consider everything as it is, and then we go to define and material. We already defined a material for a SIP-W. I just want to show you that we consider for all the overburden material a volumetric water content that is basically an overburden, as well as the other volumetric water content is rock mass 1 and rock mass 2 and sedimentary. I'm going to make it a little bit thick to make it much more visible for you guys to understand how do they look like. Then we close the tab and go to the hydraulic conductivity tab. The similar material, as you can see here, are available, and the hydraulic conductivity for these similar sort of material are already defined for these problems. I just skip this stage and show you we consider for D2 a sedimentary material. D2 and 3 are similar, and we consider for D4 and D5 a rock mass 1, and for the ore body and the rest of the material, the dike material, we consider rock mass 2. So these are the things that we need to consider for the SIP-W analysis. Now we're going to consider the boundary condition. We already defined a total head of equal to 600 meters. The only thing we need to do before that, it's good to put a point on 600 meters to do not assign the boundary condition to the higher parts. So we assigned a similar boundary condition, which is the total head equal to 600 on the line below the 600 meters that we already put a point on that area. So you can see, you simply assign them to the boundary and we are good to go. In order to resembling the in situ condition, we need to add another physics, which is basically sigma W analysis and in situ analysis. So we consider the in situ analysis as a gravity activation and the rest of the parameters as a default, as you can see in this screen. The next step is to define a fixed boundary condition both for left and right, and the bottom of the model, which is going to be fixed for both vertical and horizontal displacement. The next step is to add a stress correction analysis to redistribute the stress value which violate the failure criteria. In order to do that, we just consider all the parameters as a default value in this screen. Then we add extra steady state seepage analysis in order to model the dewatering stage for this open pit mine. Then we need to assign the right boundary condition. I consider it as simple as possible by just considering a pool water pressure equal to 0 at the bottom of the pit. So in order to do that, we just need to assign the boundary condition that I already created for the bottom of the pit. So in this case, it will calculate it, and then we just need to again assign the far field boundary condition equal to the total head of 600 meters. And then the next step is a load deformation analysis for simulating the stage of construction, actually entire excavation of 25 benches in this open pit mine. So as a parent analysis, I consider stress redistribution for this one. We need to adjust the initial and final pool water pressure. The initial one comes from the parent analysis, and the final pool water pressure comes from dewatering stage, which is the other Geostudio, and then from the other Geostudio I will select the SIP-W, which is the dewatering stage, and click OK. And I have to make sure that I toggle on the reset displacement. We are able to model the complex excavation stage by cutting the domain. Also in Leapfrog, we can include those excavation stage and import it into Geostudio. Or we can make it simple and change the cross-section stage and include just a single pit wall. But we make it simple in this example. We remove all the material which are inside the pit, and we have to make sure to remove them all the corners. And then we are going to add a finite stress space stability analysis, which is the slope W, which comes from a sigma W analysis for the right pit and the left pit. As you can see, I renamed this for the right one, and I'm going to do the similar stage and include the left one as well. The only thing we need to consider to check the slip surface, for the left it should be left to right, and for the right one should be right to left. The toggle right to left should be on. And I'm going to select the simple entry and exit slip surface. Then we just need to draw the slip surfaces and then we can adjust the point wherever we want in this one. So the entry for the exit one, I just consider the bottom of the second bench until the bottom of the pit to be the exit slip surface, to include all the local and global stability. Doing the similar one for the right pit wall, and we can include also just the limit equilibrium analysis as here for the left and the right. I just quickly rename them as a limit equilibrium left and a limit equilibrium stability analysis for the right one. The similar condition can be transported from the previous, actually the slip surface can be transported and replaced in an analysis from the previous slip surface definition that we had already, and just we transfer it into the right one. You can see I transferred the first one into the left and the second one into the right analysis. Then the only thing we need to check in the limit equilibrium analysis is all those slip surfaces are adjusted. You can see them all adjusted and all similar to the previous one that I already created. The second thing, I have to make sure that it's right to left. And the third thing, we don't need any parent analysis to be assigned for a limit equilibrium analysis. The only thing we need to adjust is the pool water pressures comes from a Geostudio analysis, which is the dewatering stage of this mine. So we adjust them both for both analysis as a dewatering stage. And then once we are done, we just toggle everything on and start running the analysis. Then we can simply check the result for first the finite element based stability analysis and for the right pit wall. And then we go into the left one. We see this is much more critical, 1.3 for the limit equilibrium analysis and 1.5 for the finite element basis. These can be considered as a good input parameters for when we want to do the strength reduction stability analysis. For doing that, we just need to consider a stress redistribution analysis and rename it into a stress reduction stability analysis, as you can see in this screen. So stress reduction stability analysis. The thing that we need to adjust, we go into the definition view and then define the project. Simply, we change the stress redistribution, a stress correction into the strength reduction stability analysis, and we adjust this parameter basically based on the finite element based stability analysis and also limit equilibrium. The rest of the parameters are identical, and we have to toggle on the reset displacement for this analysis. It worth to mention also what do we assign as a material model to all these analyses for sigma W and slope W. For sigma W, we assign a more coulomb for the overburden material. We just need to assign a unit weight, Poisson ratio, elastic modulus, cohesion, and friction angle. We assign a 0 tensile strength. For the rest of the material that you can see in this screen, all of them are a general Hook and Brown. As you can see, once I select them, the only similarity is a general Hook and Brown for them. The rest of the material, you can simply select on them and see what do we assign as a material model. So you can see as we get deeper, we have a stronger material. You can also check the similar material model into slope W. So you can see that we assigned a Hook and Brown material model for the rock mass. And as you can see, the input parameters are imported. And you can see even exporting the shear stress versus normal stress parameters. You can go even for the overburden material and see that we assign a more coulomb and the input parameters are identical. And then we close and toggle off everything and just run the analysis. You can see this is the result, the displacement on the top and a critical deviatoric stress on the bottom. You can see that the critical slip surface is almost identical to what we get out of the slope W. As a conclusion, in this month's Tech Talk, we show you how you can use Leapfrog to quickly create and update 3D geological model based on the most recent site information, and how you can use Central to have a dynamically connected workflow with a version control and as well as collaboration with the other colleagues around the world. And within the Geostudio, we show you how to use different integrated methods for cross-checking the stability analysis result. Also, it worth to mention here that there are many free resources available for Geostudio users that can be found under the Learning tab on Geostudio webpage, including manual for each product, example file with supporting documentation, tutorial video, and online training available once you sign in into your Seequent ID. You can also send a technical question via our support request. Thank you so much for your attention. Please make sure to stay connected to complete a short survey after this talk.